Hey guys, it's Dr. D-Flo and I'm back with some massive upgrades to my massive printer. We're going to cover quite a few changes, but the two most important will be swapping out the lead screws on the Z-axes for ball screws and upgrading to gear racks for the gantry. The goal is to triple the maximum print speed from 60 to 180 millimeters per second. But to take advantage of these faster travels, I need a larger printhead. My friends over at Massive Dimension graciously sent out this behemoth, the MD-PE10, which has 5 times the volumetric output of my old extruder. This beast definitely deserves its own attention, so an in-depth video is in the pipeline, but I have a lot of work to get done to achieve my ambitious print speed goals. So sit back and let's get started.
Dr. D-Flo.
It's been a year since I made a video on my printer, and there have been some improvements not related to linear motion. I want to cover those quickly. First, I moved the printer to provide more room to work on it. The printer also blocked my workbench and drawers for almost 2 years now, which was incredibly annoying. While I had the printer up in the air, I installed 9 leveling feet for better stability. During the move, I removed and recycled the ABS printed roof. Honestly, I didn't like how it looked and it reminded me of the cracked glass bed. But more importantly, its design restricted my Z travel and I need as much room as possible because the MD-PE10 extruder has a longer barrel. I will shift the Z-axis actuators up 250 millimeters to account for the barrel. With more of the weight higher up, I machined new corner pieces and added a second ring of C-beam aluminum extrusion to stabilize the top. Next, let's talk about the speed of this printer. For any 3D printer, the amount of time it takes to complete a print is limited by either the speed at which the printhead can be moved or the rate at which the extruder can melt the plastic. When printing with a small diameter nozzle, travel speed is usually the limitation. But when printing with a larger nozzle, such as this 5mm one, even a pellet extruder can struggle to melt enough plastic at high enough speeds. Let's perform a quick calculation to highlight this. My current MD-PH2 extruder can melt 1 kilogram of plastic pellets per hour, or 0.278 grams per second. If we were printing with a 5mm nozzle at a 2mm layer height and simplify the cross-sectional shape of the extruded material to be a rectangle, then our max print speed would be 22 millimeters per second. When I print in vase mode, which lays down a continuous path of material, the 60 millimeter per second max print speed of these linear actuators appears to be more than sufficient. Obviously, when I switch to the larger extruder, I will need closer to 100 millimeters per second to keep up with its 5x output. But even with my current lower throughput extruder, when printing separate objects or disconnected features, the slow non-printing moves significantly added to the total print time. Also, the longer it takes for the extruder to move across open space, the more oozing and stringing that follows. So what is limiting my max speed? That would be the 8mm lead screws that are used for all 7 of the 1500mm linear actuators. There have been many viewers rightfully point out how much these lead screws whip, especially at higher speeds. The problem with this whip is that it slowly destroys both the radial and thrust bearings on the end of each axis. Every 200 hours of printing, I had to replace the bearings on the X and Y axes. Anything above 60 millimeters per second would cause exponentially shorter bearing life. If the bearings fail during a print, they whip even more, which can loosen the nut that holds the lead screw in place. Here you're seeing the aftermath of 2 Y-axis lead screws escaping their end plates and becoming bent out of shape after crashing the gantry. Both of these lead screws had to be replaced. With the printer being able to run unintended in the background, that 200 hours flies by. So an important design consideration for the linear actuators is a more reliable and maintenance-free design. Interestingly, up until the bearings fail, whipping doesn't cause any loss of positional accuracy, at least for my setup. Yes, it does induce vibrations, but I literally have a vibrator on the printhead to keep the pellets flowing. So yes, the lead screws limit the printer's max speed and require periodic maintenance, but they are by far the most economical way to accurately move the 20-pound MD-PH2 printhead around the 4x4x4 foot build volume. Further, these C-beam linear actuators use the aluminum extrusion as both the structural member and guide for the linear motion. As you can see, the lead screw fits in this 20 by 40 millimeter gap between either side of the extrusion. This compact design maximizes print volume compared to overall machine size. When I upgrade these actuators, I don't want to lose any travel due to bulky components. I know that this is weird to say because I'm going to install a $20,000 extruder, but this linear actuator upgrade is limited by my budget. For that reason, I'm going to stick with the V-wheel system instead of upgrading to ball bearing linear guides, which could easily cost several $1,000s. While V-wheels are more inaccurate compared to linear guides, they are better at absorbing impact when the extruder nozzle runs into the part that is printing due to warping or over-extrusion. With a larger and heavier extruder, I'm going to have to take some special measures to make sure that the print pauses if the printhead collides with a growing part, but more on this later. So here are the design constraints for the new linear actuators. 1. 180 millimeter per second print speed in the XY. 2. A compact design to maximize travels. 3. Low maintenance for long prints. And 4, a somewhat tight budget, which will require machining a lot of the parts myself. I anticipate that this video will showcase the highest number of custom parts compared to any of my other content. Let's start with re-engineering the Z actuators. In normal planar 3D printing, the speed of the Z-axis matters very little. 99% of the motion occurs in the XY plane. It's only after a layer is finished that the printhead is moved up in the Z by a small amount. The lead screws worked well for the Z-axis, and I've not had to replace any of the bearings, as these actuators experience significantly less motion. However, I am concerned with my custom Teflon nut blocks that traverse the lead screws. Any kind of plastic nut will be susceptible to wear, especially when they are tasked with moving heavy loads. You can see the material coming off the nut on the lead screw. This will only get worse as the gantry becomes heavier with the new extruder. I haven't noticed any issues so far, but I want to get ahead of any problems while I'm upgrading the machine. For this reason, I've decided to switch to ball screws. If you're not familiar, ball screws have a helical groove that allows ball bearings housed within the nut to roll along. This setup has much less friction compared to a traditional nut, allowing for more efficient motion and greater longevity under heavier loads. When lubricated properly, ball screws will run almost indefinitely. But there are 2 drawbacks associated with ball screws related to my aforementioned design criteria. The first is that ball nuts must be large enough to allow the ball bearings to recirculate inside of them to allow for smooth motion. Ball nuts are much larger than traditional nuts, which is an issue because we're trying to keep the linear actuators as compact as possible. The second problem is that it can be costly to buy ball screws that don't have backlash or play in their motion. In my latest CNC mill video, I installed double nut ball screws for all 3 axes, which eliminates the gap between the ball bearings and the raceways by having 2 opposing nuts. These specialized ball nuts are more expensive and twice the size as a normal ball nut. Fortunately for this build, the ball screws will be used only for the Z-axis, and gravity naturally eliminates the play in the screw because of the weight of the gantry. So we should get accurate motion with the ball screw, but what about speed? We have previously discussed the concept of critical speed in part 2 of this series, which is the maximum speed the screw can operate at before excessive instability. Larger diameter screws can spin at faster speeds before whipping. The critical speed can also be increased by holding onto the screw tightly on both ends, which is known as the fixity of the setup. Let's start our discussion with the diameter of the screw before coming back to the fixity. If I pull one of the carriages off, you can see that the current 8mm lead screw runs between these mini V-wheels that grip the inside of the C-beam. You always want the screw and guideways to be aligned to reduce bending moments on the screw. So the diameter of the ball screw must be small enough to fit between these wheels. A 1204 ball screw, which has a diameter of 12mm and a pitch of 4mm, is as large as I can go. Compared to the old 8mm diameter lead screw, the 1204 ball screw will have a higher critical speed, but the ball nut will only move 4mm per rotation compared to the 8mm of the lead screw. Therefore, the ball screw will have to spin twice as fast to keep up. But increasing the screw diameter by 50% does not yield twice as high of a critical speed. So originally, I was expecting to have to trade the speed of the lead screw for the reliability of a ball screw. But take a look at this demo. Here we have the original lead screw actuator on the top and the new ball screw one on the bottom. The carriages are moving at the same speed, which means the ball screw is turning twice as fast. Yet it still looks more stable than the lead screw. Much more stable, in fact. This can be explained by coming back to the fixity, or how well the screw is supported on either end. If given the opportunity, a screw will move out of axis due to its uneven distribution of mass. When I previously talked about critical speed, I said that the fixity for the lead screw system was optimized for the highest speed because thrust bearings were used to pull the lead screw taut axially. Now I could talk about this for way longer than I should, but this assumption was incorrect due to some smaller details. The original actuators are designed to be easily assembled with only a couple of hex keys and an 8mm wrench, which is great for accessibility. But because everything can be slipped into place so easily, there is motion where there shouldn't be. For example, the bearings can move slightly in their pockets. Also, the lead screw diameter is 7.8mm, but a bearing with an 8mm ID is used. This may sound like a small difference, but here I have marked the inner race of the bearing. You can see that the bearing and lead screw don't turn the same speed. This is a result of the screw not being in constant contact with the bearing. Just sliding the bearing onto the end, you can see that it can twist in ways that it shouldn't. Hence, there is room for the screw to wobble at its ends, which will cause larger perturbations in the middle of the screw. To put it simply, this screw is not being supported well enough to allow for the theoretical critical speed. Not saying that this is necessarily a bad thing, just a trade-off for a low-cost and easy-to-assemble actuator. The ball screw, on the other hand, is much easier to hold tightly because it has machined or journaled ends, which are designed to fit snugly into the bearings. Also, my bearing support blocks were bored such that the bearings have to be pressed into place. There is absolutely no play here. Even though this ball screw has a larger diameter, its ability to spin twice as fast as the lead screw is largely due to the improved support on either ends. I purchased the ball screws from a faraway vendor that was offering them for a price that I couldn't pass up. They were marketed as 1500mm long ball screws, but that length included the machined ends. Therefore, these screws have about 65mm less travel than the original lead screws. I'm going to position them in the printer to make sure this travel is fully utilized. But before we get to that, let's talk about this custom carriage design, which definitely looks a little funky. Perhaps the most challenging part of incorporating ball screws in this build was getting the larger 1204 ball nut to fit. The most obvious issue was that it was unable to fit within the C opening of the extrusion. I had to shave off 1mm from the top and bottom before the ball nut would fit. This bracket allows for a right angle connection between the flange of the ball nut and the bottom of the carriage. Because the nut has to sit low in the actuator to be in line with the ball screw and V-wheels, I had to machine a cutout for it in the top of the carriage. This break in the side allows access to the grease fitting. The nut will be lubricated with EP1 grease. A future upgrade will be to include an automatic grease pump, but again, because the Z-axis moves so little during a traditional print, the relubrication interval will be quite long. The last custom components for the new ball screw linear actuators are the bearing support blocks that go on either end and the motor mounting plate. The mounting plate has a whole configuration to allow my existing NEMA 23 motors with integrated brakes to drive the ball screw. Because the barrel of the new extruder is so long, I'd be wasting quite a bit of the range of the Z actuators if they were left mounted in their previous location. I need to shift them upwards, which will be accomplished with these new 1750mm long C-beams. They are 250mm longer than the old ones. Let's get all 4 of the actuators assembled and installed on the printer.
Went up, downtown. Went up, downtown. Went up, downtown. I want to save my soul. Went up, downtown.
Okay, with that completed, we can move on to the X and Y axes, which make up the gantry. The number one priority for this upgrade is a speed of at least 180 millimeters per second. If I can't take advantage of the massive volumetric flow rate of my new extruder, why even upgrade? A ball screw with a large enough diameter to spin stably for this linear speed would be too expensive and difficult to integrate. Further, stepper motors, which are used to move all my actuators, exhibit their highest torques when operated below 1000 RPM. So any setup that requires the motors to turn at very high speeds will not have the torque required to move the printhead, which weighs more than 40 pounds or 18 kilograms when fully loaded with pellets. Servo motors are not in the financial cards at this time, and also the closed loop steppers that I have integrate nicely with my Duet control system. These constraints leave two types of actuators: belt-driven or rack and pinion. Many viewers have suggested that I use belts for faster and more efficient motion. However, the only CNC machines that I have seen use belts for work envelopes larger than a meter are CO2 laser cutters, which have very light tool heads. For heavier loads, wider belts are needed, which are difficult to tension over my 1500 millimeter actuators. If I was using a normal filament extruder, then I could get away with belts, but my pellet extruder is too heavy. For this reason, I'm going to have a go at using rack and pinion actuators. This type of linear motion system is relatively new to the Dr. D-Flo channel. We briefly explored this topic in my Mastering CNC Plasma Cutting video, where both the X and Y actuators on my industrial plasma table use this system. One of the most significant advantages of a rack and pinion transmission is its scalability and length. Unlike other systems where extended lengths can lead to issues like lead screw whip or belt stretching, a rack and pinion setup can be scaled to longer dimensions without these drawbacks. You can literally just keep lining up gear racks to any lengths you want. But let's first talk about the components, and then we will get to how I integrated them into my large format printer. As its name suggests, there are two components that make up a rack and pinion transmission. The rack is a flat linear gear with straight teeth, and the pinion is a small circular gear that can mesh with the teeth of the rack. As a motor turns the pinion, it tracks along the teeth of the gear rack, creating linear motion. The distance the pinion moves per rotation depends on the size and number of teeth. This 20-tooth pinion will travel 62.8 millimeters per rotation. Compare that to the 4 millimeters that the ball screws, which I just installed, travel, and it should be apparent that high speeds are possible with this setup. For the rack and pinion to be compatible with each other, they must share the same spacing between the teeth. The spacing and consequently the size of the teeth are related through a measurement known as the module. A larger module will correspond to larger teeth. You want a higher module for increased load capacity and durability, but of course larger teeth will take up more room. For my design, I want the rack and pinion to fit between the channel of the C-beam so that I can use my previous carriages, which have 12 V-wheels that ride on the outside of the extrusion. This wide stance of the carriage was quite rigid for the first iteration of the printer. To get both the rack and pinion to fit within this 40 millimeter gap, I have to carefully select the module and the number of teeth on the pinion. The tendency would be to pick the largest module possible for improved longevity, but then you would have to select the pinion with the fewest number of teeth to decrease its circumference so that both can fit. Pinions with low tooth counts have a lower contact ratio, which is the average number of teeth in contact between the rack and pinion. For smooth motion, you want a high contact ratio. So to balance longevity and contact ratio, I went with a 1 module rack and a 20-tooth pinion. Before moving on with the design, I do want to mention that my rack and pinion components use straight teeth, but there is another type that uses helical teeth. The angled teeth in helical racks achieve a greater contact ratio for the same number of teeth, resulting in smoother and quieter motion. Unfortunately, helical racks tend to be more expensive, but it's a potential upgrade I'm considering in the future. As previously stated, with our 20-tooth pinion, the carriage will cover 62.8 millimeters of distance for each rotation. This is almost 8 times the distance compared to the old lead screw. The larger travel distance per rotation in the rack and pinion system means that the carriage moves faster for the same rotational speed of the motor. However, this increased speed comes with a trade-off. It requires more torque to achieve the same level of force as the lead screw. To address this, I have opted for a NEMA 23 stepper motor with a 4-to-1 planetary gearbox. If the stepper motor is commanded to rotate at 1000 RPM, the output shaft on the gearbox will be spinning at 250 RPM with 4 times more torque, leading to a linear speed of 261 millimeters per second with the pinion. By starting with a 4-to-1 ratio, I aim to strike a balance between achieving the necessary torque and maintaining the stepper motor within its efficient operating speed. I can still upgrade to a 5-to-1 or 6-to-1 if I need more torque without falling short of my 180 millimeter per second speed goal. Unfortunately, a planetary gearbox can affect the accuracy of the linear actuator. If I rotate the shaft back and forth, you can hear the small amount of play between the gears. The datasheet for this motor states that there is up to 1.5 degrees of backlash. Assuming the worst case scenario, we would lose 260 microns or 10 thou of motion every time the carriage switches directions. This is one of the reasons why a belt reduction is often used to get greater mechanical advantage for rack and pinion systems compared to a planetary gearbox, as you don't have this high of reversal error. Personally, I like the simplicity of the gearbox, and my motion controller can electronically compensate for this backlash, so this is not a big concern at the moment. Shortly, we will conduct tests to measure the total positioning error of the system. But first, there's one last source of backlash that can be addressed: the small gap existing between the meshing teeth of the rack and pinion. Ideally, this backlash can be eliminated through sophisticated design solutions like split pinion or dual pinion drives. However, these methods are complex and costly. A more straightforward, yet less recommended method involves using a tensioner to force the pinion more tightly into the rack. While this approach is cost-effective, it's not without drawbacks. Forcing the teeth to mesh more deeply can lead to uneven wear and potentially shorten the lifespan of the system due to increased stress on the gear teeth. I'm not sure how much shorter of a life there will be, but I do know that this is a popular approach for DIY machines that use rack and pinion. My carriage design includes this swivel plate that uses a shoulder bolt and bronze sleeve to allow for the motor and pinion to be pulled closer to the gear rack by this long M8 bolt. This spring placed between the M8 bolt and the swivel plate will set the tension. In addition to decreasing backlash, this tension arm setup allows for the pinion to move away from the gear rack if there's debris stuck in the teeth. The alternative would be binding of one side of the gantry, causing significant damage. I will mount the gear rack upside down to decrease the likelihood that something gets stuck in the teeth. Okay, next we need to mount the gear racks. Gear racks can be purchased in a range of sizes, but I found the most economical to be 500 millimeter or 20-inch lengths. The linear actuators are 1500 millimeters long, so 3 racks must be mounted in a row to realize the full travel of each axis. If you plan to use gear racks in series, you should purchase racks with machined ends. These models have tooth forms correctly configured at the ends to minimize the space between racks to maximize contact area when the pinion transitions between segments. However, I found that opting for machined ends would cost 5 times the price as compared to ordinary saw-cut racks. At the time of purchase, I couldn't justify this premium because there was still quite a few question marks around my design. So I purchased really cheap gear racks. I paid about $15 per 500 millimeter section, and it's impressive how terrible these ends are. I would have assumed that the easiest place to cut a gear rack would be right in the valley between the teeth, but each one of these was cut at a different location. It'll be quite easy to swap in higher quality gear racks in the future because they fasten directly to the C-beam with M4 screws. Even with their sketchy ends, I can align 2 racks by meshing them both with a third one. With the racks attached, I would like to point out that this is a different C-beam than used previously. It's known as a C-beam heavy, and it has 2.7 times the wall thickness of a regular C-beam. The C-beam heavy will be used for both the X and Y actuators and should be more resistant to the bending and twisting that occurs from moving larger loads, such as the MDPE-10 extruder. Here I have my test rig for the rack and pinion. Before we move it around, I will tighten a tensioner on the carriage until I feel no play between the pinion and the gear rack. For a conservative first test, I will move the carriage at 60 millimeters per second, which was the old max speed of the printer. Okay, I'm actually quite surprised how smooth the motion is. Rack and pinions are not known for being quiet due to the friction between the gear teeth, but this is definitely a manageable noise level. I don't see excessive vibrations or anything else that would be a red flag. Now let's try our target print speed of 180 millimeters per second. Wow, no issues at all. I know that you can imagine that 180 millimeters per second is 3 times faster than 60 millimeters per second, but I'm going to overlay these two speeds on top of each other just to emphasize how much more productive this printer will be once we get these new actuators installed. Even though the carriage is not carrying any load, let's see what its max speed is. It looks like 400 millimeters per second is where it tops out at. At 450, the motor stalled. This excess speed is great news. It means that I can step up to a higher gear ratio if I need more torque for faster accelerations. So the speed is where I want it to be, but this rack and pinion actuator would not be very helpful if I can't position the printhead accurately. The first measurement that I will take is the amount of backlash present. I've already removed the play from the rack and pinion, but let's see if the planetary gearbox causes 1.5 degrees or 260 microns of lost motion. To measure this, I have installed a dial indicator and moved the carriage within its range. Next, I will move the carriage slightly to the left and zero the indicator. Now I'm going to move the actuator 1 millimeter to the right. The indicator reading is 0.768 millimeters, which means there is 0.232 millimeters of backlash. I'm now going to move the carriage back 1 millimeter to the left. The indicator reading goes back to nearly zero. This means that the backlash is consistent on both sides, which is good news. Backlash only shows up when you switch directions. To demonstrate this, I will move 1 millimeter to the right, then zero the indicator, and then move it to the right another 1 millimeter. The indicator reads 0.992 millimeters, which is off by 8 microns. Not bad. Let's zero it again and move it another 1 millimeter to the right. 0.990 millimeters is the reading. That small amount of deviation from 1 millimeter could be from the indicator not being perfectly in line with the carriage, but either way, the movements are accurate enough for my application. The way backlash compensation works is whenever the carriage switches directions, the controller has the motor rotate an extra amount to take up this slop. In this case, an extra 0.232 millimeters. The Duet motion controller that I used just recently supported backlash compensation, which is great for this application. Before we assemble the rest of the rack and pinion actuators, let's take a look at the CAD model to see how the gantry will come together. Even though the carriages are quite large, when I toggle on the visibility of the extruder, you get a sense of just how massive the MDPE10 is. Because I was worried about the X-axis sagging over the print bed, I have incorporated a second heavy C-beam to span this distance. Each C-beam will have its own carriage with rack and pinion transmission. These two carriages will be tied together and joined to the extruder. More on this connection later. You can see that the X actuators attach the backside of the two Y carriages. My goal here was to try and keep the weight of the extruder in line with the Y carriages to prevent them from experiencing high twisting forces, but this was the best I could do with the sheer size of this extruder. Now that you see how this will come together, let's get to the assembly. I'm pumped with how well the gantry came together. I'm going to move the printer around while I'm talking so you can get a feel for how loud it is in respect to my voice. Again, typically a drawback of rack and pinion is the noise, but as you can hear, while perhaps a bit louder than the lead screws, this upgrade is not going to get me in trouble with the neighbors. It's amusing to see how high the gantry can go. This is the same travel as the old design, but as mentioned, I moved up the actuators about 250 millimeters or 10 inches to account for the longer barrel of the new extruder. However, preserving the original travels on the X and Y axes proved to be more difficult. In fact, I'm going to take a pretty heavy loss on the Y axis travels because the printhead consumes a lot more space than the previous design. In a rack and pinion setup, the motors must ride along with the carriage, which causes the X-axis motors to stick out the back. Further, my planetary gearbox motors are not the most space conscious. Of course, the new extruder is an even bigger space hog. I could make some changes to the enclosure to allow the motors to stick out the back or the extruder out the front, but as is, I will have 956 millimeters or 37 inches of usable travel in the Y. For the X-axis, I decided to get a little creative in maximizing the travel. As you can see, we have a similar problem where the Y-axis motors are obstacles pointing inwards. Without any modification, the printhead travels will be severely restricted by these opposing motors on either side. But what if the extruder was offset from the X-axis carriages so that it could pass over the motor when moving left or right? This thought is why I made the bottom carriage plate shorter than the rest. It can travel under the Y motors unscathed. You can probably imagine how far the extruder will have to be away from the X-axis carriage to pass over a majority of the Y-axis motors. This design choice could put a lot of pressure on the X-axis carriages as they try and support a cantilevered printhead. My backup plan will be to just mount the extruder closer and lose X-axis travel. I also mentioned in the beginning of the video that special measures would need to be taken to pause the printer if the extruder collides with a print that is warped and shifted upwards. The extruder's offset from the X carriages provides plenty of room to incorporate a floating head system that will allow the extruder to move up if it encounters an obstacle, which would trigger a switch to stop the print. Let's hop into my CAD file to see how I have both maximized the X-axis travel and implemented a floating head design. Here you can see there are two pairs of HD25 rails mounted on both X-axis carriages. Under normal circumstances, the weight of the extruder will pull these guideways to the bottom of their travel. But if a failed print pushes the extruder up, then this switch will be triggered. An additional aluminum spacer is needed to provide clearance for the Y-axis motors. Then we have the extruder mounting plate, and finally the extruder. This creates a rather heavy assembly, and I didn't want the failed print to have to exert the equivalent of 40 pounds or 18 kilograms of force to move the printhead up to trigger the switch. So I have included a gas strut that will offload 30 pounds or 14 kilograms. This gas strut will eventually contact the Y-axis motor, limiting travel, but it can be removed when I need to maximize print area. Now that you understand where the pieces go, let's put together the printhead. You have to admit that it's pretty satisfying watching the printhead pass over the Y-axis motors to preserve as much X-axis travel as possible. I'm glad that worked out, but perhaps what is more impressive is that the printer can still achieve my 180 millimeter per second print speed goal even with the 40-pound extruder in tow. My dual X-axis setup seems to have enough power and rigidity to move this beefy printhead around. Honestly, if that didn't work out, it would have been back to the drawing board and you wouldn't have gotten a Dr. D-Flo YouTube video in 2024. I kid, but all signs point to my next video being a game changer because I'm gonna get to plug this new extruder in and print outrageously large objects even quicker. So on that note, get subscribed if you're not already and hit that like button if you made it this far in the video. I'm gonna leave you with a montage of one of the carriage plates being machined from start to finish, and with that, I'll catch you in the next one.